we're at time to start. I will make people feel guilty about not coming out and running down the hall later on. We should get started. So it's my pleasure to introduce today's Colloquium speaker, Dana Yang. So Dana got her PhD at Duke or at Yale, and then spent some time at Duke as a postdoc. And then some time at Simons. Did you overlap with Mansi while you were there?
Yeah, that's very much.
So very good. And today we'll be talking about learner private convex optimization. With that, I'll hand it over to you.
Thank you so much for the introduction. Yeah, I'm super thrilled to be here to talk about my work on learner private convex optimization. So this is joint work with my amazing postdoc advisor, Jiaming Xu from Duke Business School, and my wonderful collaborator, Hong Xu from Stanford Graduate School of Business. So to start, let's look at this cartoon. So by the way, this work, I wouldn't say it's mathematically that deep at all, but I really like the story behind it, so enjoy. So basically, the framework can be captured in this cartoon. Nowadays, it's becoming more and more common where when a learner is trying to train a model, it's training this model by interacting with thousands and nowadays even millions of users. And these users, they could have their own end devices, for example, each user's individual's mobile phone. And the learner tries to train a central model by broadcasting sequences of queries and receiving sequences of responses. Right? So how it works is that the learner at each iteration of an algorithm submits a model parameter, which is a query. The users receive the model parameter, they look at it, and then based on their own local data, they do some local computations and decide to send the learner back a response that's a function of the query and their local data set. Then the learner can aggregate all the responses, use the aggregated response to update the query, and then send out the next step of the next iteration of the model parameters, which is the next query. So they go back and forth like this until the learner arrives at a model that is good in the sense that maybe it minimizes some population risk function. So now imagine a scenario where maybe out of these thousands or millions of users, maybe they're not all that angelic participants, right? If one of them or many of them are actually these adversaries who are merely participating in this model training process in order to steal your model parameters, okay? Since you're broadcasting your sequence of model parameters to all the users, it's so easy for the adversary to just go in there and eavesdrop and steal your model, which could be very expensive to train. So our question is, in scenarios like this, how do you query in a smarter way so that you protect yourself from such an eavesdropping attack? Okay. Note that this notion of privacy, sort of differs from the current focus of the privacy literature, which focuses on protecting the data privacy of the learners, usually by, say, data privacy of the users, where the users, they choose to, in the response, maybe add some noise in order to protect the privacy of their local data. But here we're considering a completely different problem where we focus on protecting the privacy of the learner. And as a result, our problem formulation and definition of privacy and also our privacy preserving mechanism is also going to be significantly different from the current differential privacy literature. Another motivating example is a pricing example where a central learner could be a company that's trying to launch a product, is conducting market surveys to users to decide what's the optimal price to launch this product at. So they can do iterations of market research, but if an adversary participates in these iterations of research, then they can also easily steal the final release price of that product. And if the adversary is potentially from a competing company with a similar product to launch, you see how that can be very detrimental. So it's actually of great importance to protect the learner's privacy, not just the user's privacy. So that's the story. And we formulate this problem using the simplest formulation you can think of. So suppose the learner is trying to learn an optimal model parameter, here denoted as an x star. It's a one-dimensional number, real number between 0 and 1. So it cannot get simpler than that. So the learner is trying to learn x star. For example, x star could be the optimal launch price. And the adversary is also trying to learn x star. But there is this asymmetry of information here. So the learner submits queries, receives responses, and pretty much observes everything that's happening in this process. The adversary, however, we assume only sees the queries and does not see the responses. And that's because in the previous slide, remember that the learner has access to a lot more information than the adversary does. Because the adversary, they only have access to their own local dataset, which contains a negligibly small amount of information compared to what the learner gets, which is the aggregated response from all the users. So for simplicity, we're just assuming that the adversary does not see the aggregated response at all. So this is the formulation. This model was actually first proposed in an earlier paper by Peng Xu and his collaborators, Tsitsiklus and Zhi. And they focus on the setting where the response is just a binary, say, aggregated response, telling you whether or not the true x star is to the right or to the left of this query. So it's like a game of 20 questions. Right, except now there's a slight twist because there is an adversary that's also in play. So in an earlier work in 2020 with my collaborators, what we did is in the case of binary responses, we characterize the sharp trade-off between privacy and accuracy and the efficiency of the search. And later in the talk, I'm going to actually quantify what I mean by sharp characterization. But this is when the response is binary, which is a very simple setting. Later, in a paper that's published this year, we extended this simple model to the framework of convex optimization, where the unknown x star is actually the minimizer of some convex function that's supported between 0 and 1. And the response, instead of being just a binary response telling you which direction is x star, it actually tells you the full gradient of the unknown convex function evaluated at the query. So it's like you're doing convex optimization in a sequential way using first-order feedback. Okay, so as you can imagine, this is a much more closer approximation to real-life learning settings where a lot of times you are trying to find or optimize a convex loss function. Okay, so the talk outline is for the first part, I'm going to focus on the binary search model where the response is just binary, because actually even from this simple model, we can see a lot of the intricate interplay between the two parties, the adversary and the learner, and it actually inspires a lot of the design of our private algorithms for the convex optimization problem. And then we'll talk about the additional difficulties in the framework of convex optimization. Okay, but first, just binary search. We have a learner and adversary. They're playing this game of 20 questions. Both are trying to approximate this unknown x star. So if, say, the learner does not have any privacy constraint, then the optimal algorithm to use, of course, is the bisection algorithm. Basically, you first ask, is x star larger than a half? If it is, you query 3/4. If it isn't, you query 1/4. And you narrow down the range of x star by half using each query. And you cannot get more efficient than that. That's going to cost log 1/epsilon queries to locate x star into an epsilon length interval. But you can see that query strategy is not private at all, because simply by taking the last query that the learner submits, the adversary can get a fairly good idea of where X star is, because inevitably the learner is going to get closer and closer to X star. Right? So this is no good. It's not private at all. On the other extreme, you can consider a completely private algorithm, which is the grid search. Right? So you divide the interval from 0 to 1 into epsilon length subintervals, and you query all the endpoints of the subintervals. So it takes 1 over epsilon queries. It's very expensive. However, this is completely private because from the queries, right, you ask 1 over epsilon, 2 over epsilon, and so on. The adversary cannot obtain any information from this sequence of queries. So this is completely private, but very, very expensive. So our question is, what's that sweet spot in the middle where we are satisfying our requirements on accuracy, on privacy, and also we want the querying to be as efficient as possible. Okay. So to do that, we need to quantify a few things. First of all, let's quantify accuracy. And here, this is just a very natural definition of accuracy. We say a learner's estimator is accurate if, with probability 1, it can approximate X star up to an additive error of epsilon over 2. Right? So basically, you want to narrow down the range of X star into an epsilon length interval. So that's what this definition is saying. So for the bisection search, it takes log 1 over epsilon queries to achieve epsilon accuracy. And for grid search, the cost is 1 over epsilon. Now, to define privacy, though, it's slightly more complicated. And we actually consider 2 different formulations, where X star is random and where X star is deterministic. So under the Bayesian setting, where X star is, we're just assuming it to be distributed uniformly between 0 and 1, then we say querying strategy is delta L private, right? So we quantify the level of accuracy using 2 parameters now, delta and L. So it means that if a strategy is private if no estimator from the adversary can approximate X star up to delta over 2 additive error with probability larger than 1 over L. So in other words, we say something is private when the adversary cannot succeed very often. And we also consider deterministic setting because when X star is deterministic and unknown, it no longer really makes sense to talk about this probability over X star. So instead, the quantification we use is using the so-called information set. Basically, it's a set of all possible X star that could lead to the query sequence that's seen by the adversary. So if this set has a large delta covering number, then we say that this strategy is delta L private. In other words, we're basically saying if there are L possible places that are delta apart from each other, and all these L places could possibly lead to the final query sequence, then we say that this strategy is private, is delta L private. Yes?
Sorry, I want to make sure I understand X star. So since this is basic for everything else you're telling
Yes.
us about. So in your example, we're figuring out the price point that the users are comfortable with for the new product.
Yes.
For some users, they are, and for others, they are not. Is X
Exactly.
star deterministic? Is it stochastic?
Yeah. So like X star in that example, I would say, for example, if the company is shooting for the optimal price, like the highest price such that over half of the consumers in the consumer base would purchase this product, suppose that's what they're estimating as an example. Of course, in reality, maybe we even want to extend this model into maybe more realistic online pricing models where maybe your ultimate goal is not just to find this sweet spot X star, where maybe you want to also optimize your revenue, right? So like you want to maximize X star and times like the number of consumers who are going to buy it. So this is like a very idealistic simplification of what happens in real life. But there are basically what I want to say is depending on the real application, like the two settings, one may be more applicable than another. Usually, so it's not clear from this, but we're going to see that the deterministic characterization of privacy is actually a lot more stringent on the adversary. So it's more applicable when the adversary is more like risk averse, basically. Okay. So under both settings, this is how we quantify the efficiency of the search. We define the optimal query complexity as the minimum number of queries that's necessary to achieve epsilon accuracy and delta privacy at the same time. And in order to precisely characterize the trade-off, we need to figure out how does this optimal query complexity behave as a function of epsilon, delta, and L, where we call that epsilon quantifies accuracy and delta and L quantify privacy. So let's focus on the Bayesian setting first. This is the result that we obtained under the Bayesian setting. We show that the optimal query complexity is sandwiched between these upper and lower bounds. And I would like to point out that our upper and lower bounds only differ in this sign. So here we have +1 in the upper bound and -1 in the lower bound. So these bounds are rather tight. They only differ by an additive factor of 4n. We have this assumption that delta needs to be between q epsilon and 1/2L, and it's actually a very natural assumption because imagine on one extreme, if delta is smaller than q epsilon, right? So even if the learner uses the most efficient strategy, which is bisection search, then even by taking the last query of the bisection search, it could still be q epsilon away from x star, right? So that's the direction it goes. So in this case, the adversary just cannot estimate at all, and obtaining privacy becomes trivial. On the other end, if delta is larger than 1/2L, well, let's imagine if delta is larger than 1/L, right? Then what happens is the adversary can just guess x star, say I guess x star is equal to 1/2. And naturally, from the uniform prior distribution of x star, there is going to be delta probability of 1/2 being delta/2 close to the true x star. So if delta is larger than 1/L, it again does not really make sense to talk about price. Yes?
So I guess one of the things that I should have asked on the previous slide, you're considering stochasticity and what x star might be, but you're considering deterministic probing protocols. Are the queries ever partly random?
Oh yeah, that's a great question. So the queries can be randomized. The learner's estimator can be randomized, and the adversary can also randomize their estimation strategy. So in the paper, we are more careful with this. We quantify the randomness used by the learner as in some outside random variable y that's distributed between 0 and 1. So when we're doing all the analysis, we need to carry this y around. But it doesn't actually bring that much more complexity to the analysis. Yeah, that's a great question. Okay. Yeah. So, in short, we show that under the Bayesian setting, the optimal query complexity behaves like this term. It's log 1/L epsilon plus L multiple of delta over epsilon. So I would like to focus on two asymptotic regimes to talk about how does this optimal query complexity behave, because we actually see some very interesting phase transition. So Suppose delta and epsilon, they go to 0 at the same time, proportionally at the same rate. So this is saying, this is saying the adversary is required to estimate roughly just as well as the learner does, right? So this is a very high requirement on the adversary. When this is the case, it would become easier to protect privacy, right? Because life is harder on the adversary. And we find that the optimal query complexity is log 1 over epsilon, which is the cost, which is the number of queries you need if there's no privacy constraint. And then there's an additive factor, L times log of a constant. And there's another constant factor. So in this regime, the cost of privacy is essentially an additive factor of L. In the other regime, where delta maybe scales like a constant and epsilon goes to 0, so this is saying no matter how accurate the learner is estimating, we still want to prevent the adversary from estimating, say, within 0.1 accuracy. So in this case, protecting privacy becomes a much harder task. And we find that the cost of privacy now changes from an additive factor in L now to a multiplicative factor in L. So we see sort of this phase transition as delta grows. So I'd like to talk a little bit about the querying strategy that we designed to achieve this optimal query complexity. So we adopt this two-stage querying strategy, where one stage is the pure learning phase. So the algorithm contains two stages. We're saying in the first stage, let's not care about privacy at all. Let's not worry about that. Because at this point, we don't even know that much about where X star is. So let's not worry about hiding it. And let's just run the most efficient algorithm we know, which is bisection. And we first locate X star up to a subinterval of length L times delta. Okay. Now that we're semi-close to X star, in the next stage of the algorithm, we worry about preserving privacy. Okay. So the way we preserve privacy, this is actually an idea that was also used in Kwong and his co-author's previous paper. It's through replication. So from the picture here, right, in the first picture, we use bisection to locate X star into an interval I. Now let's zoom in to this interval I and split it into L subintervals of equal length. Now let's query all the endpoints of these subintervals. After querying these endpoints, the learner is going to receive the responses, and the responses are going to tell the learner which subinterval contains the true X star. In this example, the learner knows that X star is between Q6 and Q7, but the adversary does not know that. Now, using symmetry and replication, the learner preserves privacy as follows. They run bisection inside of the subinterval from Q6 to Q7. But in parallel, they're running replicated bisection in the other subintervals as well. So specifically, it works like this. The learner submits the first batch of queries. So that's all the queries with number 1 in a circle below. So they query all the midpoints of all the subintervals. Now they look at the response to the midpoint that's in the interval that contains X star. And if they know that X star is larger than this query, then for the next batch of queries, they query the 3/4 point of each subinterval. And that way, the learner is able to locate X star eventually to epsilon accuracy. But the adversary, without knowing which subinterval contains X star, now has L possible locations for where X star could be, and they're all delta apart. And because of symmetry, the adversary does not really have any additional information of which subinterval is more likely to contain X star. And that's why the adversary would not be able to approximate X star up to an interval of length delta over 2 with probability larger than 1 over L. So this is a very natural idea of using replication to achieve privacy. Now to the lower bound, because we still want to obtain a matching lower bound. The lower bound idea is also very simple, although I think it's a little bit more intricate. Basically, we want to design a strategy of the adversary that is somewhat smart, because we are playing this two-party game between the learner and the adversary. So we want to design an intelligent adversary that the learner cannot easily beat. Because remember that the learner has to beat all possible adversaries' strategy in order to make things private. The particular strategy that we consider is called the truncated proportional sampling strategy. So suppose the adversary is just going to disregard the first k queries. It throws the first k queries away and only samples from the queries, the k plus 1 query up to the final query. And it's going to sample from the uniform empirical information of those queries, and using that sampled query as its estimator X tilde. And this strategy seems a little bit wasteful at first glance because it's throwing away information that could be useful, right? But the intuition behind that is those first k queries, actually they're not really that likely to be close to the true X star anyways, because the learner is also in the stage of learning. So, so this is the intuition, and it turns out that the adversary is not throwing away that much information by doing this truncation, and it actually gives a much improved lower bound when you truncate. So the lower bound proof can basically be summarized in one slide. Firstly, we're trying to, the adversary's probability of success, that's the adversary being close, being delta over 2 close to X star. If the adversary is sampled proportionally from the queries qk plus 1 up to qn, then this probability is simply the expected number of queries that are in the interval X star minus delta over 2 to X star plus delta over 2. And if we move some terms, we automatically get a lower bound on the number of queries n, which is k plus L multiple of the expected number of queries inside of that interval that's symmetric around X star. So this proof sort of is saying that the lower bound has to account for two terms. The first term k is sort of the number of queries that the learner has to submit anyways in order to get semi-close to X star. Then there is an additive cost. There's a cost of searching within the delta length interval surrounding X star. But that cost needs to be multiplied by L to preserve privacy. Now we're going to choose an optimize over k to choose an approximate k. In this case, it's going to be log 1 of L delta. And we find a lower bound on the expected queries from qk plus 1 to qn. And that number is just going to be close to the total expected number of queries inside of this interval, because we argue that in the first k star queries, q1 to qk, they are not going to be, not many of them are going to be close to X star anyways on average. So the total number of queries that are needed to narrow down the range of X star in a delta length interval into an epsilon length interval is roughly log delta over epsilon. So that's why, combining all the terms, we have the number of queries is at least the first k plus L multiple of log delta over epsilon. Now notice here, a very interesting phenomenon is that k star, the number of queries that the adversary disregards, is actually the same as the number of queries that the learner submits in the first stage of the optimal query complexity. Okay? Remember, the learner has a first pure learning phase, and the learner also submits this many queries. So it sort of shows up this elegant duality between the learner and the adversary. Okay, so that was the Bayesian setting. I want to quickly talk about the deterministic setting as well. Under the deterministic setting, we also see a similar phase transition where the query complexity, depending on how large delta is, behaves differently. And but regardless of which regime we're in, we find out that the cost in preserving privacy is actually always at most an additive factor of L. So in this sense, preserving privacy under the deterministic setting is a much simpler task than the Bayesian setting. And the reason for that is basically because under the Bayesian setting, the adversary also knows that X star has a uniform prior distribution, and that prior knowledge can actually, the adversary can leverage that and sort of do posterior updates and run estimation schemes based on the learner's querying strategy, and they can form probabilistic guesses on where X star could be. But when the adversary does not have that kind of prior distribution information, it makes their task harder, and it makes it easier for the learner to deceive the adversary. As a matter of fact, we will see that the learner can very easily deceive the adversary by planting possible locations of X star along the way. And without the ability to update the posterior distribution of X star, the adversary cannot roll out any of those planted locations. And that's how we achieve privacy. So let me quickly go through the query strategy under the deterministic setting. It also contains two phases. In the first phase, the learner submits L guesses. So each guess is just a pair of queries that are epsilon apart. For example, the learner first submits a query at a half and another query at a half plus epsilon. After submitting that pair of queries, two things could happen. One, the learner learns that, okay, I guessed correctly, the X star is actually inside of this tiny epsilon length interval. And if I don't care about privacy, I'm done. But since I care about privacy, I need to keep going. The other case is the learner finds out, okay, this guess was incorrect. I need to keep querying to locate X star. So again, the learner needs to keep going. So from the point of view of the adversary does not know what's going on and cannot rule out the possibility of X star being contained in this little subinterval. Okay. So in the first phase of the learning, phase, the learner is going to submit in total L guesses like this. So that effectively plants L possible locations for X star, and each of them could potentially contain X star. And the adversary, under this setting, has no way of ruling them out. And the learner plants those queries, plants these guesses in a way such that all these guesses are at least delta apart. Now after these L guesses, now note that the learner wants to be efficient, so as they're submitting the guesses, they're also narrowing down the range of X star as well. So after the L guesses, learner should narrow down the range of X star into a small-ish interval. And we find the length of that interval is going to be q to the power minus L or delta, depending on the regime of delta. Then inside of this subinterval I, the learner just does pure learning, basically by running bisection. So you see the query strategy here is actually very different from the Bayesian setting. It's almost reversed. So the learner achieves privacy in the first stage and then does learning in the second stage. And that's basically because in this setting, it's actually much easier to plant guesses in order to deceive the adversary. So the learner does not need to achieve privacy via replication. And the total number of queries submitted is in the first stage, they submit 2 L queries for the L guesses, and then there's a cost associated with running bisection. And that number depends on the value of delta. Okay. I would like to quickly comment that we do extend our results under the Bayesian setting to noisy responses as well. So maybe instead of the binary response, you receive a response that's noisy, that's flipped, that's flipped through a probability channel with probability P. So when this happens, we need to come up with other definitions of accuracy because the learner can no longer achieve accuracy with probability 1. So we come up with 2 different notions, whether, so one is learner is accurate on average, or the learner is accurate with high probability. And for both notions, we're able to attain, characterize the optimal query complexity in terms of all the parameters. And our bounds are all accurate up to multiplicative constants. Okay, so now I would like to move on to the second part of the talk, which is suppose instead of observing the binary responses, we actually are trying to optimize a convex function, and the response now is the gradient of the unknown convex function. Okay. So again, this is the model. This is the problem formulation. We assume there is a family of real-valued convex functions supported on 0, 1, and there is some true convex function in that family. The learner submits a sequence of queries, receives a sequence of responses that are the first-order gradients. And we also, as before, we assume that the adversary only observes the queries and not the responses. So we use the same definition of accuracy. For privacy, we again consider 2 settings. One, where the unknown convex function is distributed according to some prior distribution, and the other where the convex function is deterministic and unknown. So I definitely find the Bayesian setting to be a lot more interesting and a lot more challenging to study as well. So the first challenge actually arises when we're even trying to formulate this problem. What is a prior distribution on the family of convex functions that makes sense under this setting? Right? So in fact, even without any privacy constraints, if you just talk about convex optimization in the Bayesian framework, that area is still relatively unexplored. And it could be partly due to just the difficulty of coming up with a prior distribution that makes sense. So let me explain. As a simplest example, we can consider a prior distribution over the family of all quadratic functions. And then we can place prior distributions on the coefficients of the quadratic function. However, this prior distribution is clearly not sophisticated enough because simply by querying 2 arbitrary points, the learner can pretty much just solve for the coefficients. And well, it cannot solve for ABC, but it can solve for A and B, and therefore it can learn what is the optimizer X star by just querying 2 points. So that would sort of trivialize the optimization problem. And pretty much by the same reason, any parametric prior distribution is not really going to make too much sense. Okay. So in the field of Bayesian nonparametrics, one prior distribution that was proposed in 2011 by Hannah and Danson was constructed as follows. So since each convex function is basically the supremum of all the affine functions that sit beneath it. So they model this convex function as the mass of countably many linear pieces. So we tried that prior as well, but it turned out even if this distribution has countably many parameters, still, eventually with high probability, what determines the minimizer is just going to be where two specific linear pieces meet. And it turns out that it's actually pretty easy with high probability for the learner to locate which two linear pieces as well. So again, the optimization problem becomes kind of trivial. In a word, all these prior distributions lack some level of complexity. And we want to find a prior distribution that captures this complexity of the family of convex functions that would make the problem of convex optimization an interesting problem. So to do that, our prior distribution is actually going to rely on the Dirichlet process. If you probably know it because you are in applied math, but if you haven't seen this, it's basically a distribution on distribution functions. So it's a process that's commonly used for modeling probability distributions, or it's a distribution on cumulative distribution functions. So it's flexible enough in the sense that it comes with a parameter alpha that characterizes the smoothness of the convex functions. And a very nice property about the Dirichlet process is that it's naturally self-similar. So if you have a CDF that follows a Dirichlet process and you zoom in condition on the value of the CDF at two endpoints, then inside of this interval between the two endpoints, the function is still going to follow a Dirichlet process, maybe just scaled and shifted. Okay? And that nice similarity property makes this a natural prior distribution with the complexity structure that we want to use for optimization problem. It's like no matter which points you query, when you zoom in, you still are not going to be that certain about where the minimizer is. So to model the convex function, the idea is very simple because the Dirichlet process is a prior distribution on CDFs. So CDFs are all monotone functions increasing from 0 to 1. So convex functions, they have gradients that are monotone functions. So we simply model, place a prior over a bunch of CDFs and set the first order derivative of our unknown convex function to be a shifted and scaled function of this random CDF. And that's our prior distribution. And turns out to have just the level of complexity to produce some interesting results. In short, we find that the number of the optimal query complexity under this prior distribution is sandwiched between these upper and lower bounds. And these bounds in many parameter regimes are actually tied up to multiplicative constants. For example, in a regime where delta and L are constants, we find that the optimal query complexity behaves like a constant multiple of L times log 1 over epsilon. And when there are no privacy constraints, we find that the optimal query complexity behaves like multiple of log 1 over epsilon, which note that log 1 over epsilon is exactly the cost of binary search. So this result, even without the talk of privacy, I think is interesting on its own as just a result on Bayesian optimization. And I guess the takeaway after seeing this result is just that, or how were we able to show this result, is just that we want to show that the learner cannot search faster than binary search. So here, note that the learner is actually given a lot more information. The learner is not just given the binary directional information, it's given the full gradient. So we sort of want to argue that that additional information does not really help the learner that much. And that's actually the key idea behind our lower bound proof, where we define a good probability event on which the learner cannot obtain information faster than as if they're just given binary directional responses. And the upper bound proof is a modified version of the replicated bisection algorithm, except now the prior distribution on X star is no longer uniform, so we need to keep track of that as well. So I guess that's about almost all that I'm going to talk about. There is another, so there's this another notion of privacy where the unknown function, convex function, is deterministic, and basically the difference is that instead of wanting X star, wanting the adversary to succeed in an average sense, here we require the adversary to succeed in a minimax sense. And as I was mentioning before, this is more applicable when the adversary is very risk averse. And it turns out that in this setting, we see a similar phenomenon as the binary search problem, where the optimal query complexity is much smaller compared to the Bayesian setting. The price you pay for privacy is, again, at most 2L, so it's an additive factor. And that's again because under the minimax setting, the requirement on the adversary is a lot more stringent, and it makes things easier. It makes it easier for the learner to preserve privacy, and that is reflected in our upper and lower bounds. So some open questions. We want to extend this guide to D dimensions, especially in the Bayesian setting, but the first difficulty is really we cannot come up with the prior distribution that naturally extends the derivative process into multiple dimensions. Another direction is can we consider randomized gradient response as well? For example, can we prioritize the stochastic gradient descent algorithm? And I think those are interesting questions to pursue. Thank you, and I'll leave the remaining time for questions.
Questions?
Yes.
So, suppose the adversaries comprise a sizable portion of your answers or whoever is providing the information.
Yeah.
Then they can aim to distort your answer to some degree in addition to learning what the true answer should have been. Have you considered this setting? Does it make sense?
Yeah, I think it makes sense. We briefly considered it, but we didn't come up with a formulation that was easy to analyze. So I think it would be like, so we consider noisy responses in this setting. However, what you're describing is the noise could be adversarial as well. Right? So that's a very interesting direction. I have no idea how to analyze it.
Well, there is a lot of work with adversarial noise. The question is, I guess, does it make sense to combine it with trying to learn?
Yeah.
And it doesn't seem to be, right? In some sense, it seems to be a contradictory goal.
I don't know. I could be trying to feed you this information and while figuring out the true answer to your question.
But is it possible? That's the question.
I don't know.
Yeah.
That's why I asked.
You have to have, it's a game theoretic question. Like, is there a strategy for the adversary that actually will achieve both?
Yeah.
That's a good question.
Yeah, it's a great question. Yeah, I really don't know. It's very open. Yes.
So, a completely different direction. The Bayesians, for binary search, in the Bayesian setting you get, in some sense, much more information because you've got a prior, but you were only considering uniform prior. Do you have a hypothesis about if I gave you a non-uniform prior and told you something like its entropy, would that, could you get similar bounds but with a multiplicative factor that's based on entropy or something?
I think possibly, very possibly. So here actually in the convex optimization problem, we have something similar to that because here the distribution over X star is also not uniform. And the bounds, so the leading constants, they're not going to depend, let me call the constant here. The C1, like constants like this. So they don't really depend on the entropy. Maybe what the tide constant would be, but here the constant depends on sort of the lowest point of the density of X star. Okay, so it's like if you have a uniform lower bound on the density, then it's going to work. But in general, I think it would be possible to have a tight bound that's information theoretic because our lower bound is an information theoretic proof using Fanel's inequality. So I assume it's possible. I don't know exactly.
Other questions?
So is there any way to draw inference on whether the learner is genuine or person based on the way they respond?
Oh, so that's you're saying when the user they can like feed maybe wrong responses to the learner and how do or
Yeah, so basically, like, for example, if someone is genuine and wants to learn efficiently, they will do this binary
yes.
and then, well, I'm just curious, like, is there a way to, like, defend and draw inference to know who is the person, whether this is the person, whether you
Oh, so like to test whether or not the learner is doing a private scheme or just
yeah. Maybe it's not so relevant.
No, it's a good question. Yeah, I haven't considered that. I'm thinking usually when the learner is running gradient descent, I assume it will be pretty obvious. Yeah, or if the learner is throwing queries like all over the place, then maybe you can also learn. Yeah, but we haven't considered that part yet. But that's interesting. That's like you're viewing the problem from the other perspective, from the adversary. You're trying to see, is the learner trying to trick? Yes.
So I can imagine, so you've done the binary search, which is sort of it's the natural algorithm, right? I can also imagine something that has the sort of optimal complexity, same as binary search, and is perfectly private if I'm allowed to change the type of query by instead asking, what's the kth bit, right? So if my query was not, are you greater than or less than some threshold, but
I
are
see.
you what is the kth bit?
Yeah,
which
yeah.
still is sort of, is bisecting your space in
Yeah,
different
yeah,
ways.
yeah, it is.
Then it's completely, I always ask what's the first bit, second bit, third bit, et cetera, right?
That's interesting. Yeah.
So I wonder if you thought at all about, are there different query families that provide better balance, provide better privacy for the same number of queries?
I see. That's really interesting. I would think, yeah, actually, I think we briefly did consider this, but we didn't really pursue. I think it would be easier to preserve privacy if you're allowed to ask queries like that. Say if you're asked to ask about like the kth bit of the binary expansion, then that just effectively it does the replication for you. So it splits the interval into sub-intervals, and then like if the adversary does not see the response to the kth bit, then there are just two possibilities the adversary can never rule out. So I think that would make the strategy easier. Even like the learner can even just run the bisection algorithm by querying all the bits and still be private.
So I can imagine what that would look like for binary search.
Yeah.
I don't know what it would look like actually for the convex optimization side.
Yeah. So what would that be? So instead of querying the ith bit, I don't know.
Fair.
I don't know. Yeah, well, we should talk offline. That's a really interesting direction.
Yeah. Are there any sort of boundary effects that come into play, at least in either the Bayesian setting or in the convex setting? I mean, when you have sort of like a parameter space that might have a boundary or not?
Yeah. I mean, they don't come into play that much, but there are some like plus minus ones that are results of those. Like those places near 0 or 1 that are just tricky to deal with.
Right. I mean, I guess to like David's point, you know, if you had a situation where you might not have a uniform prior on there, I mean, do you anticipate that that might be more salient, I guess, like the non-uniform or the boundary effects, right? Because you could kind of get pushed into a corner, like maybe.
Yeah. I assume that could be the case. Yeah, if like your prior distribution is more concentrated near the endpoints, that might. I would be very surprised if it has any really significant effect on the bound, though.
Yeah.
This is from the boundary.
Cool.
Yes.
I'm a bit confused about the concept. If the query to each user has to be the same in each iteration.
Oh yeah. So we're assuming that the learner submits all the same queries to all the users. Yeah, but it's actually, this is a great question. It's a very interesting extension to consider if the learner submits different queries. Because nowadays in federated learning, actually each user's end device has their own model, submodel, their own model parameters. Yeah, so that would make the problem a lot more complicated.
Much more privacy or like regulated in that way. So if you're doing a boundary, so you just ask each one, is it?
Yeah, exactly.
And I also wonder, like, why does it make sense to like send the same inquiry to different users? Is that because each user has different data, or there's some mechanism now?
Yeah, so we're assuming each user has a different data set, but they could, for example, come from the same probability distribution. And the learner is trying to optimize, say, a convex function on the population level. So it's like, for example, the minimizer of the empirical risk function for all the data.
So in general, do we really need to say that they're users? We can just abstract the setting as I am querying a function, and I don't want my queries to reveal the optimal solution. Isn't that?
Yeah, exactly,
right.
yeah. So yeah, we're trying to optimize it from, the modern machine learning point of view to motivate it. Yeah, but I feel like there are a lot more applications besides like model training and pricing.
We are at time, so there's refreshments in the camp space for after, and let's thank Dunn again.
Oh my God. Somebody always. That was a really good. Yeah.
I like your
It seems like there are several
Oh, it's been around for like.
How are you?